The Age of AI and Our Human Future. Henry A. Kissinger, Eric Schmidt, Daniel Huttenlocher. Audiobook presented by the Learner's Library. Chapter 3, From Turing to Today, and Beyond. Chapter 4, Global Network Platforms. Chapter 3, From Turing to Today, and Beyond. In 1943, WHEN researchers created the first modern computer, electronic, digital, and programmable. Their achievement gave new urgency to intriguing questions. Can machines think? Are they intelligent? Could they become intelligent? Such questions seemed particularly perplexing given long-standing dilemmas about the nature of intelligence. In 1950, mathematician and code-breaker Alan Turing offered a solution. In a paper unassumingly titled, Computing Machinery and Intelligence, Turing suggested setting aside the problem of machine intelligence entirely. What mattered, Turing posited, was not the mechanism but the manifestation of intelligence. Because the inner lives of other beings remain unknowable, he explained, our sole means of measuring intelligence should be external behavior. With this insight, Turing sidestepped centuries of philosophical debate on the nature of intelligence. The imitation game he introduced proposed that if a machine operated so proficiently that observers could not distinguish its behavior from a human's, the machine should be labeled intelligent. The Turing test was born. Many have interpreted the Turing test literally, imagining robots that pass for people, if that should ever happen, as meeting its criteria. When pragmatically applied, however, the test has proved useful in assessing intelligent machines' performance in defined, circumscribed activities, such as games. Rather than requiring total indistinguishability from humans, the test applies to machines whose performance is human-like. In so doing, it focuses on performance, not process. Generators like GPT-3 are AI because they produce text similar to text people produce, not because of the specifics of their models. In GPT-3's case, the fact that it was trained using vast amounts of online information. In 195. 6. Computer scientist John McCarthy further defined artificial intelligence as machines that can perform tasks that are characteristic of human intelligence. Turing's and McCarthy's assessments of AI have become benchmarks ever since, shifting our focus in defining intelligence to performance, intelligent-seeming behavior, rather than the term's deeper philosophical, cognitive, or neuroscientific dimensions. While for the past half-century, machines have largely failed to demonstrate such intelligence, that impasse appears to be at its end. Having operated for decades on the basis of precisely defined code, computers produced analyses that were similarly limited in their rigidity and static nature. Traditional programs could organize volumes of data and execute complex computations, but could not identify images of simple objects or adapt to imprecise inputs. The imprecise and conceptual nature of human thought proved to be a stubborn impediment in the development of AI. In the past decade, however, computing innovations have created AIs that have begun to equal or exceed human achievement in such fields. AIs are imprecise, dynamic, emergent, and capable of learning. AIs learn by consuming data, then drawing observations and conclusions based on the data. While previous systems required exact inputs and outputs, AIs with imprecise function require neither. These AIs translate texts not by swapping individual words but by identifying and employing idiomatic phrases and patterns. Likewise, such AI is considered dynamic because it evolves in response to changing circumstances and emergent. because it can identify solutions that are novel to humans. In machinery, these four qualities are revolutionary. Consider, for example, the breakthrough of AlphaZero in the world of chess. Classical chess programs relied on human expertise, developed by human play, being coded into their programming. But AlphaZero developed its skills by playing millions of games against itself, from which it discovered patterns for itself. The building blocks of these learning techniques are algorithms, sets of steps for translating inputs, such as the rules of a game or measures of quality of moves within those rules, into repeatable outputs, such as winning the game. But machine learning algorithms are a departure from the precision and predictability of classical algorithms, including those in calculations like long division. Unlike classical algorithms, which consist of steps for producing precise results, machine learning algorithms consist of steps for improving upon imprecise results. These techniques are making remarkable progress. Aviation is another example. Soon, AI will pilot or co-pilot a variety of vehicles in the air. In the DARPA program Alpha Dogfight, AI fighter pilots have outperformed humans in simulated combat by executing maneuvers beyond the capabilities of human pilots. Whether piloting jets to fight wars or drones to deliver groceries, AI is poised to have significant impact on the future of both military and civilian aviation. Although we have seen only the beginnings of such innovations, already, they have subtly altered the fabric of human experience. And in the coming decades, the trend will only accelerate. Because the technological concepts driving the AI transformation are as complex as they are important, this chapter will be devoted to explaining both the evolution and current state of various types of machine learning and use, both startlingly powerful and inherently limited. A basic introduction to their structure, capabilities, and limitations is vital to understanding the social, cultural, and political changes they have already brought as well as the changes they are likely to produce in the future. The evolution of AI. Humanity has always dreamed of a helper, a machine capable of performing tasks with the same competence as a human. In Greek mythology, the divine blacksmith Hephaestus forged robots capable of performing human tasks, such as the bronze giant Talos, who patrolled the shores of Crete and protected it from invasion. France's Louis XIV in the 17th century and Prussia's Frederick the Great in the 18th century harbored a fascination for mechanical automata and oversaw the construction of prototypes. In reality, however, designing a machine and rendering it capable of useful activity, even with the advent of modern computing, has proved devilishly difficult. A central challenge, it turns out, is how, and what, to teach it. Early attempts to create practically useful AIs explicitly encoded human expertise, via collections of rules or facts, into computer systems. But much of the world is not organized discretely or readily reducible to simple rules or symbolic representations. While in fields that do use precise characterization, chess, algebraic manipulation, and business process automation, AI made great advances. In other fields, like language translation and visual object recognition, inherent ambiguity brought progress to a halt. The challenges of visual object recognition illustrate the shortcomings of these early programs. Even young children can identify images with ease. But early generations of AI could not. Programmers initially attempted to distill an object's distinguishing characteristics into a symbolic representation. For example, to teach AI to identify a picture of a cat, developers created abstract representations of the various attributes, whiskers, pointy ears, 4 legs, a body, of an idealized cat. But cats are far from static. They can curl up, run, and stretch, and manifest various sizes and colors. In practice, the approach of formulating abstract models and then attempting to match them with highly variable inputs thereby proved virtually unworkable, because these formalistic and inflexible systems were only successful in domains whose tasks could be achieved by encoding clear rules. From the late 1980s through the 1990s, the field entered a period referred to as AI winter. Applied to more dynamic tasks, AI proved to be brittle, yielding results that failed the Turing test, in other words, that did not achieve or mimic human performance. Because the applications of such systems were limited, R&D funding declined, and progress slowed. Then, in the 1990s, a breakthrough occurred. At its heart, AI is about performing tasks, about creating machines capable of devising and executing competent solutions to complex problems. Researchers realized that a new approach was required, one that would allow machines to learn on their own. In short, a conceptual shift occurred. We went from attempting to encode human distilled insights into machines to delegating the learning process itself to the machines. In the 1990s, a set of renegade researchers set aside many of the earlier era's assumptions, shifting their focus to machine learning. While machine learning dated to the 1950s, new advances enabled practical applications. The methods that have worked best in practice extract patterns from large datasets using neural networks. In philosophical terms, AI's pioneers had turned from the early Enlightenment's focus on reducing the world to mechanistic rules, to constructing approximations of reality. To identify an image of a cat, they realized, a machine had to learn a range of visual representations of cats by observing the animal in various contexts. To enable machine learning, what mattered was the overlap between various representations of a thing, not its ideal. In philosophical terms, Wittgenstein, not Plato. The modern field of machine learning, of programs that learn through experience, was born. Modern AI. Significant progress followed. In the 2000s, in the field of visual object recognition, when programmers developed AIs to represent an approximation of an object, by learning from a set of images, some of which contained the object, some of which did not, the AIs identified the objects far more effectively than their coded predecessors. The AI used to identify hallucin illustrates the centrality of the machine learning process. When MIT researchers designed a machine learning algorithm to predict the antibacterial properties of molecules, training the algorithm with a dataset of more than 2,000 molecules, the result was something no conventional algorithm, and no human, could have accomplished. Not only do humans not understand the many connections AI revealed between a compound's properties and its antibiotic capabilities, but even more fundamentally, the properties themselves are not amenable to being expressed as rules. A machine learning algorithm that improves a model based on underlying data, however, is able to recognize relationships that have eluded humans. As previously noted, such AI is imprecise in that it does not require a predefined relationship between a property and an effect to identify a partial relationship. It can, for example, select highly likely candidates from a larger set of possible candidates. This capability captures one of the vital elements of modern AI. Using machine learning to create and adjust models based on real-world feedback, modern AI can approximate outcomes and analyze ambiguities that would have stymied classical algorithms. Like a classical algorithm, a machine learning algorithm consists of a sequence of precise steps. But those steps do not directly produce a specific outcome, as they do in a classical algorithm. Rather, Modern AI algorithms measure the quality of outcomes and provide means for improving those outcomes, enabling them to be learned rather than directly specified. Neural networks, inspired by, but, due to complexity, not entirely patterned after, the structure of the human brain, are driving most of these advances. In 1958, Cornell Aeronautical Laboratory researcher Frank Rosenblatt had an idea. Could scientists develop a method for encoding information similar to the method of the human brain, which encodes information by connecting approximately 100 billion neurons with quadrillions, 1015, of synapses? He decided to try. He designed an artificial neural network that encoded relationships between nodes, analogous to neurons, and numerical weights, analogous to synapses. These are networks in that they encode information using a structure of nodes, and the connections between those nodes, in which designated weights represent the strength of the connections between nodes. For decades, a lack of computing power and sophisticated algorithms slowed the development of all but rudimentary neural networks. Advances in both fields, however, have now liberated AI's developers from these restrictions. In the case of Halocene, a neural network captured the association between molecules, the inputs, and their potential to inhibit bacterial growth, the output. The AI that discovered Halocene did this without information about chemical processes or drug functions, discovering relationships between the inputs and outputs through deep learning, in which layers of a neural network closer to the input tend to reflect aspects of the input while layers farther from the input tend to reflect broader generalizations that are predictive of the desired output. Deep learning allows neural networks to capture complex relationships such as those between antibiotic effectiveness and aspects of molecular structure reflected in the training data, atomic weight, chemical composition, types of bonds, and the like. This web allows the AI to capture intricate connections, including connections that can elude humans. In its training phase, as the AI receives new data, it adjusts the weights throughout the network. The network's precision, then, depends on both the volume and quality of the data on which it is trained. As the network receives more data and is composed of more network layers, the weights begin to more accurately capture the relationships. Today's deep networks typically contain around 10 layers. But neural network training is resource-intensive. The process requires substantial computing power and complex algorithms to analyze and adjust to large amounts of data. Unlike humans, most AIs cannot simultaneously train and execute. Rather, they divide their effort into two steps: training and inference. During the training phase, the AI's quality measurement and improvement algorithms evaluate and amend its model to obtain quality results. In the case of Halocene, this was the phase when the AI identified relationships between molecular structures and antibiotic effects, based on the training set data. Then, in the inference phase, researchers tasked the AI with identifying antibiotics that its newly trained model predicted would have a strong antibiotic effect. The AI, then, did not reach conclusions by reasoning as humans reason, it reached conclusions by applying the model it developed. Different tasks, different learning styles. Because the application of AI varies with the tasks it performs, so, too, must the techniques developers use to create that AI. This is a fundamental challenge of deploying machine learning. Different goals and functions require different training techniques. But from the combination of methods, machine learning algorithms, neural networks, and learning techniques, new possibilities such as cancer spotting AIs emerge. As of this writing, 3 forms of machine learning are noteworthy: supervised learning, unsupervised learning, and reinforcement learning. Supervised learning produced the AI that discovered hallucin. To recap, when MIT researchers wanted to identify potential new antibiotics, they used a 2,000-molecule database in order to train a model in which molecular structure was input and antibiotic effectiveness was output. Researchers presented the AI with the molecular structures, each labeled according to its antibiotic effectiveness. Then, given new compounds, the AI estimated the antibiotic effectiveness. This technique is called supervised learning because the AI developers used a dataset containing example inputs, in this case, molecular structures, that were individually labeled according to the desired output or result, in this case, effectiveness as an antibiotic. Developers have used supervised learning techniques for many purposes, such as creating AIs that recognize images. For this task, the AIs train on a set of pre-labeled images, learning to associate an image with its appropriate label, for example, the image of a cat with the label cat. Having encoded the relationship between images and labels, AIs are then able to correctly identify new images. Therefore, when developers have a dataset that indicates a desired output for each set of inputs, supervised learning has proved to be a particularly effective way of creating a model that can predict outputs in response to novel inputs. In situations where developers have only troves of data, however, they can employ unsupervised learning to extract potentially useful insights. Thanks to the Internet and the digitization of information, businesses, governments, and researchers are awash in data, which they can access more easily than they could in the past. Marketers have more customer information, biologists more DNA data, and bankers more financial transactions on file. When marketers want to identify their customer base, or when fraud analysts seek potential inconsistencies among reams of transactions, unsupervised learning allows AIs to identify patterns or anomalies without having any information regarding outcomes. In unsupervised learning, the training data contains only inputs. Then programmers task the learning algorithm with producing groupings based on some specified weight of measuring the degree of similarity. For example, streaming video services such as Netflix use algorithms to identify clusters of customers with similar viewing habits, in order to recommend additional streaming to those customers. But fine-tuning such algorithms can be complex, because most people have several interests. They are typically grouped within several clusters. AIs trained through unsupervised learning can identify patterns that humans might miss because of the pattern's subtlety, the scale of the data, or both. Because such AIs are trained without specification regarding proper outcomes, they can, not unlike the human autodidact, produce surprisingly innovative insights. However, both the human autodidact and these AIs can produce eccentric, nonsensical results. In both unsupervised and supervised learning, AIs chiefly use data to perform tasks such as discovering trends, identifying images, and making predictions. Looking beyond data analysis, researchers sought to train AIs to operate in dynamic environments. A third major category of machine learning, reinforcement learning, was born. In reinforcement learning, AI is not passive, identifying relationships within data. Instead, AI is an agent in a controlled environment, observing and recording responses to its actions. Generally, these are simulated, simplified versions of reality lacking real-world complexities. It is easier to accurately simulate the operation of a robot on an assembly line than it is in the chaos of a crowded city street. But even in a simulated, simplified environment, such as a chess match, a single move can trigger a cascade of opportunities and risks. As a result, directing an AI to train itself in an artificial environment is, in general, insufficient to produce the best performance. Feedback is required. Providing that feedback is the task of the reward function, indicating to the AI how successful its approach was. No human could effectively fill this role. Running on digital processors, AIs can train themselves hundreds, thousands, or billions of times within the space of hours or days, making direct human feedback wholly impractical. Instead, programmers automate such reward functions, carefully specifying precisely how the function operates and the nature of how it simulates reality. Ideally, the simulator provides a realistic experience, and the reward function promotes effective decisions. AlphaZero's simulator was straightforward. It played against itself. Then, to assess its performance, it employed a reward function that scored its moves based on the opportunities they created. Reinforcement learning requires human involvement in creating the AI training environment. Even if not in providing direct feedback during the training itself, humans define a simulator and reward function, and the AI trains itself on that basis. For meaningful results, careful specification of the simulator and the reward function is vital. The power of machine learning. From these few building blocks, myriad applications arise. In agriculture, AI is facilitating the precise administration of pesticides, the detection of diseases, and the prediction of crop yields. In medicine, it is facilitating the discovery of new drugs, the identification of new applications of existing drugs, and the detection or prediction of future maladies. As of this writing, AI has detected breast cancer earlier than human doctors by identifying subtle radiological indicators. It has detected retinopathy, one of the leading causes of blindness, by analyzing retinal photos. It has predicted hypoglycemia in diabetics by analyzing medical histories, and it has detected other heritable conditions by analyzing genetic codes. In finance, AI is equipped to facilitate high-volume processes, loan approval or denial, acquisitions, mergers, declarations of bankruptcy, and other transactions. In other fields, it is facilitating transcription and translation, in some ways, the most compelling illustration of all. For millennia, humanity has been challenged by the inability of individuals to communicate clearly across cultural and linguistic divides, mutual miscomprehension, and the inaccessibility of information in one language to a speaker of another, has caused misunderstanding, impeded trade, and fomented war. In the story of the Tower of Babel, it is a symbol of human imperfection, and a bitter penalty for human hubris. Now, it seems, AI is poised to make powerful translation capabilities available to wide audiences, potentially allowing more people to communicate more easily with one another. Up through the 1990s, researchers attempted to devise rules-based language translation programs. While their efforts had some success in laboratory settings, they failed to yield good results in the real world. The variability and subtlety of language did not reduce to simple rules. All this changed when, in 2015, developers began to apply deep neural networks to the problem. Suddenly, machine translation leaped forward. But its improvement did not just derive from the application of neural networks or machine learning techniques. Rather, it sprang from new and creative applications of these approaches. These developments underscore a key point. From the basic building blocks of machine learning, developers have the capacity to continue innovating in brilliant ways, unlocking new AIs in the process. To translate one language to another, a translator needs to capture specific patterns, sequential dependencies. Standard neural networks discern patterns of association between inputs and outputs, such as the sets of chemical properties those antibiotics typically possess. But such networks do not, without modification, capture sequential dependencies, such as the likelihood that a word will appear in a certain position in a sentence given the words that came before it. For example, if a sentence begins with the words, "I went to walk the next word is far more likely to be dog than cat or airplane. To capture these sequential dependencies, researchers devised networks that use as inputs not only still-to-be translated text, but also text that has already been translated. That way, the AI can identify the next word based on sequential dependencies in the input language and in the language the text is being translated to. The most powerful of these networks are transformers, which do not need to process language from left to right. Google's BERT, for example, is a bidirectional transformer designed to improve searching. Additionally, in a considerable shift from conventional supervised learning, language translation researchers employed parallel corpora, a technique in which specific correspondence between inputs and outputs, for example, meaning between texts in two or more languages, is not needed for training. In conventional approaches, developers trained AI using texts and their pre-existing translations. After all, they had the requisite level of correspondence between one language and another. Yet this approach greatly limited the amount of training data as well as the types of text available. Although government texts and best-selling books are frequently translated, periodicals, social media, websites, and other informal writings generally are not. Rather than restricting AIs to training on carefully translated texts, researchers simply supplied articles and other texts in various languages covering a single topic, declining to bother with detailed translations between them. This process, training AIs on roughly matching, but untranslated, bodies of text, is the parallel corpora technique. It is akin to stepping from an introductory language class into a total immersion program. The training is less precise, but the volume of available data is much bigger. Developers are able to include news articles, reviews of books and movies, travel stories, and virtually any other formal or informal publication on a topic covered by writers in many languages. The success of this approach has led to more general use of partially supervised learning, in which highly approximate or partial information is used to train. When Google Translate began to employ deep neural networks trained using parallel corpora, its performance improved by 60%, and it has continued to improve ever since. The radical advancement of automated language translation promises to transform business, diplomacy, media, academia, and other fields as people engage with languages that are not their own more easily, quickly, and cheaply than ever before. Of course, the ability to translate texts and classify images is one thing. The capacity to generate, to create, new text, images, and sounds is something else. Thus far, the AIs we have described excel at identifying solutions: a chess victory, a drug candidate, a translation good enough to use. But another technique, generative neural networks, can create. First, generative neural networks are trained using text or images. Then they produce novel text or images, synthetic but realistic. To illustrate, a standard neural network can identify a picture of a human face, but a generative network can create an image of a human face that seems real. Conceptually, they depart from their predecessors. The applications of these so-called generators are staggering. If successfully applied to coding or writing, an author could simply create an outline, leaving the generator to fill in the details. Or an advertiser or filmmaker could supply a generator with a few images or a storyboard, then leave it to the AI to create a synthetic ad or commercial. More concerningly, generators might also be used to create deep fakes, false depictions, indistinguishable from reality, of people doing or saying things they have never done or said. Generators will enrich our information space, but without checks, they will likely also blur the line between reality and fantasy. A common training technique for the creation of generative AI pits two networks with complementary learning objectives against each other. Such networks are referred to as generative adversarial networks or GANs. The objective of the generator network is to create potential outputs, while the objective of the discriminator network is to prevent poor outputs from being generated. By analogy, one can think of the generator as being tasked with brainstorming and the discriminator as being tasked with assessing which ideas are relevant and realistic. In the training phase, the generator and discriminator are trained in alternation, holding the generator fixed to train the discriminator and vice versa. These techniques are not flawless. Training GANs can be challenging and often can produce poor results, but the AIs they yield can achieve remarkable feats. In their most common form, AIs trained with GANs may suggest sentence completions when drafting emails or permit search engines to complete partial queries. More dramatically, GANs may be used to develop AIs that can fill in the details of sketched code. In other words, programmers may soon be able to outline a desired program and then turn that outline over to an AI for completion. Currently, GPT-3, which can produce human-like text, see Chapter 1, is one of the most noteworthy generative AIs. It extends the approach that transformed language translation to language production. Given a few words, it can extrapolate to produce a sentence, or given a topic sentence, can extrapolate to produce a paragraph. Transformers like GPT-3 detect patterns in sequential elements such as text, enabling them to predict and generate the elements likely to follow. In GPT-3's case, the AI can capture the sequential dependencies between words, paragraphs, or code in order to generate these outputs. Trained on vast amounts of data drawn primarily from the Internet. Transformers also can transform text into images and vice versa, expand and condense descriptions, and perform similar tasks. Today, the quality of GPT-3's output, and that of similar AIs, can be impressive but can vary widely. Sometimes, their output appears highly intelligent, at other times, silly or even completely unintelligible. And yet Transformers' basic function has the potential to alter many fields, including creative ones. Therefore, they are the subject of considerable interest as researchers and developers probe their strengths, limitations, and applications. Machine learning has not only broadened the applicability of AI, it has also revolutionized AI even in areas where previous approaches, such as symbolic and rules-based systems, were successful. Machine learning methods have taken AI from beating human chess experts to discovering entirely new chess strategies. And its capacity for discovery is not limited to games. As we mentioned, DeepMind built an AI that successfully reduced the energy expenditures of Google's data centers by 40% more than what its excellent engineers could achieve. This and other advances are taking AI past what Turing envisioned in his test, performance. Indistinguishable from human intelligence, to include performance that exceeds humans, thereby pushing forward the frontiers of understanding. These advances promise to allow AI to handle new tasks, to make AI more prevalent, and even to allow it to generate original text and code. Of course, Whenever a technology becomes more potent or prevalent, challenges accompany these developments. The personalization of searching, the online function most of us employ most often, is illustrative. In Chapter 1, we described the difference between a traditional internet search and an AI-run internet search as the difference between being exposed to designer clothes and being exposed to the full range of clothes available for purchase. An AI enables this outcome, a search engine tailoring itself to an individual user, in two ways. 1. After receiving queries, such as things to do in New York, an AI can produce concepts, such as walk in Central Park and see a show on Broadway, and 2. AI can remember the things a search engine has been asked before and the concepts it has, in response, produced. In addition, it can store these concepts in its version of memory. Over time, it can use its memory to produce concepts that are increasingly specific and, theoretically, increasingly helpful to its users. Online streaming services do the same, using AI to make suggestions of television shows and movies more focused, more positive, or more anything that people want them to be. This can be empowering. AI can steer children away from mature content and, at the same time, toward content appropriate for their ages or frames of reference. AI can steer all of us away from content that is violent, explicit, or otherwise offensive to our sensibilities. It depends on what the algorithms, after analyzing users' past actions, deduce those users' preferences to be. As AI gets to know people, the outcome is largely positive. Subscribers to streaming services, for example, become increasingly likely to stream shows and movies that interest rather than offend or confuse them. The proposition that filtration can help steer choices is both familiar and practical. In the physical world, tourists in foreign countries may hire guides to show them the most historic sites or the most meaningful sites according to their religions, nationalities, or professions. But filtration can become censorship through omission. A guide can avoid slums and high-crime areas. In an authoritarian country, a guide can be a government minder, and thus only show a tourist what the regime wants him or her to see. But in cyberspace, filtration is self-reinforcing. When the algorithmic logic that personalizes searching and streaming begins to personalize the consumption of news, books, or other sources of information, it amplifies some subjects and sources and, as a practical necessity, omits others completely. The consequence of de facto omission is twofold: it can create personal echo chambers, and it can foment discordance between them. What a person consumes, and thus assumes reflects reality, becomes different from what a second person consumes, and what a second person consumes becomes different still from what a third person consumes. A paradox we consider further in Chapter 6. Managing the risks that increasingly prevalent AI will pose is a task that must be pursued concurrently with the advancement of the field, and it is one of the reasons for this book. We all must pay attention to AI's potential risks. We cannot leave its development or application to any one constituency, be it researchers, companies, governments, or civil society organizations. AI's limits and management. Unlike earlier generations of AI, in which people distilled a society's understanding of reality in a program's code, contemporary machine learning AIs largely model reality on their own. While developers may examine the results generated by their AIs, the AIs do not explain how or what they learned in human terms. Nor can developers ask an AI to characterize what it has learned. Much as with humans, one cannot really know what has been learned and why, though humans can often offer explanations or justifications that, as of this writing, AI cannot. At best, we can only observe the results an AI produces once it has completed its training. Accordingly, humans must work backward. Once an AI produces a result, people, be they researchers or auditors, must verify that the AI is producing the results desired. Sometimes, operating beyond the bounds of human experience and unable to conceptualize or generate explanations, AI may produce insights that are true but beyond the frontiers of, at least current, human understanding. When AIs produce unexpected discoveries in this fashion, humans may find themselves in a similar position to that of Alexander Fleming, the discoverer of penicillin. In Fleming's lab, a penicillin-producing mold accidentally colonized a petri dish, killing off disease, causing bacteria and cluing Fleming into the existence of the potent, previously unknown compound. At the time, humanity, lacking a concept of an antibiotic, did not understand how penicillin worked. The discovery launched an entire field of endeavor. AIs produce similarly startling insights, such as identifying drug candidates and new strategies for winning games, leaving it to humans to divine their significance and, if prudent, integrate these insights into existing bodies of knowledge. In addition, AI cannot reflect upon what it discovers. Across many eras, humans have experienced war, then reflected on its lessons, its sorrows, and its extremes. From Homer's account of Hector and Achilles at the gates of Troy in the Iliad to Picasso's portrayal of civilian casualties in the Spanish Civil War in Guernica. AI cannot do this, nor can it feel the moral or philosophical compulsion to do so. It simply applies its method and produces a result, be that result, from a human perspective, banal or shocking, benign or malignant. AI cannot reflect. The significance of its actions is up to humans to decide. Humans, therefore, must regulate and monitor the technology. The inability of AI to contextualize or reflect like a human makes its challenges particularly important to attend to. Google's image recognition software has infamously mislabeled images of people as animals and animals as guns. These errors were plain to any human but eluded the AI. Not only are AIs incapable of reflection, they also make mistakes, including mistakes that any human would regard as rudimentary. And while developers are continually weeding out flaws, deployment has often preceded troubleshooting. Such misidentifications stem from several sources. Dataset bias is one problem. Machine learning requires data, without which AIs cannot learn good models. A critical problem is that without careful attention, it is more likely that problems of insufficient data will occur for underrepresented groups such as racial minorities. In particular, facial recognition systems have often been trained on datasets with disproportionately few images of Black people, resulting in poor accuracy. Both the quantity and coverage matter. Training AIs on large quantities of highly similar images will result in neural networks that are incorrectly certain of an outcome, because they have not encountered it before. In other high-stakes situations, similar underspecification can occur. For example, datasets for training self-driving cars may contain relatively few examples of extraordinary situations, such as when a deer leaps across the road, leaving the AI underspecified as to how to deal with such a scenario. Yet in such scenarios, the AI has to operate at peak levels. Alternatively, AI bias may result directly from human bias, that is, its training data may contain bias inherent in human actions. This can occur in the labeling of outputs for supervised learning, whatever misidentification the labeler makes, deliberate or inadvertent, the AI will encode. Or a developer may incorrectly specify a reward function used in reinforcement training. Imagine an AI trained to play chess on a simulator that overvalues a set of moves favored by its creator. Like its creator, that AI will learn to prefer those moves, even if they fare poorly in practice. Of course, the problem of bias in technology is not limited to AI. The pulse oximeter, which has become an increasingly pertinent measurement of two metrics of health, heart rate and oxygen saturation, since the start of the COVID-19 pandemic, overestimates oxygen saturation in dark-skinned individuals. By assuming the way light skin absorbs light is normal, its designers effectively assumed the way dark skin absorbs light is abnormal. The pulse oximeter is not run by AI. But still, it fails to pay sufficient attention to a particular population. When AI is employed, we should seek to understand its errors, not so we can forgive them but so we can correct them. Bias besets all aspects of human society, and in all aspects of human society, merits a serious response. Another source of misidentification is rigidity. Consider the case of an animal being misidentified as a gun. The image misleads AIs because it contains subtle characteristics that humans do not detect but AIs can, and can be confused by. AI does not possess what we call common sense. It occasionally conflates two objects that humans could quickly and easily distinguish. Often, what and how it conflates is unexpected, not least because, as of this writing, the robustness of AI auditing and compliance regimes is poor. In the real world, an unexpected failure can be more harmful, or at least more challenging, than an expected one. Society cannot mitigate what it does not foresee. AI's brittleness is a reflection of the shallowness of what it learns. Associations between aspects of inputs and outputs based on supervised or reinforcement learning are very different from true human understanding. With its many degrees of conceptualization and experience, the brittleness is also a reflection of AI's lack of self-awareness. An AI is not sentient. It does not know what it doesn't know. Accordingly, it cannot identify and avoid what to humans might be obvious blunders. This inability of AI to check otherwise clear errors on its own underscores the importance of developing testing that allows humans to identify the limits of an AI's capacities, to review its proposed courses of action, and to predict when an AI is likely to fail. Accordingly, the development of procedures to assess whether an AI will perform as expected is vital. Since machine learning will drive AI for the foreseeable future, humans will remain unaware of what an AI is learning and how it knows what it has learned. While this may be disconcerting, it should not be. Human learning is often similarly opaque. Artists and athletes, writers and mechanics, parents and children, indeed, all humans, often act on the basis of intuition and thus are unable to articulate what or how they learned. To cope with this opacity, societies have developed myriad professional certification programs, regulations, and laws. Similar techniques should be applied to AIs. For example, societies could permit an AI to be employed only after its creators demonstrate its reliability through testing processes. Developing professional certification, compliance monitoring, and oversight programs for AI, and the auditing expertise their execution will require, will be a crucial societal project. In industry, pre-use testing exists on a spectrum. App developers often rush programs to market, correcting flaws in real time, while aerospace companies do the opposite, test their jets religiously before a single customer ever sets foot on board. The variance in these regimes depends on several factors, above all, the inherent riskiness of the activity. As AI deployments multiply, the same factors, inherent riskiness, regulatory oversight, market forces, will likely distribute them across the same spectrum, with AIs that drive cars being subjected to significantly greater oversight than AIs that power network platforms for entertainment and connection, such as TikTok. The division between the learning and inference phases in machine learning permits a testing regime like this to function. When an AI learns continuously, even as it operates, it can develop unexpected or undesirable behavior, as Microsoft's chatbot infamously did in 2016. On the internet, Tay encountered hate speech and quickly began to mimic it, forcing its creators to shut it down. Most AIs, though, train in a phase distinct from the operational phase, their learned models. The parameters of their neural networks are static when they exit training. Because an AI's evolution halts after training, humans can assess its capacities without fear that it will develop unexpected, undesired behaviors after it completes its tests. In other words, when the algorithm is fixed, a self-driving car trained to stop at red lights cannot suddenly decide to start running them. This property makes comprehensive testing and certifications possible. Engineers may vet a self-driving AI's behavior in a safe environment before uploading it into a car, where an error could cost lives. Of course, fixity does not mean that an AI will not behave unexpectedly when set in novel contexts. It simply means that pre-testing is possible. Auditing datasets provides another quality control check. By ensuring that a facial recognition AI trains on diverse datasets, or that a chatbot trains on datasets stripped of hate speech, developers can further reduce the risk that the AI will falter when made operational. As of this writing, AI is constrained by its code in 3 ways. First, the code sets the parameters of the AI's possible actions. These parameters might be quite broad, permitting a substantial range of autonomy and therefore risk. A self-driving AI can brake, accelerate, and turn, any of which could precipitate a collision. Nevertheless, the parameters of the code establish some limits on the AI's behavior. Though AlphaZero developed novel chess strategies, it did not do so by breaking the rules of chess. It did not suddenly move pawns backward. Actions outside the parameters of the code are beyond the AI's vocabulary. And if the programmer does not put the capacity there, or explicitly forbids the action, the AI cannot do it. Second, AI is constrained by its objective function, which defines and assigns what it is to optimize. In the case of the model that discovered halicin, the objective function was the relationship between the molecule's chemical properties and their antibiotic potential. Limited by its objective function, that AI could not have instead sought to identify molecules that might, for example, help cure cancer. Finally, and most obviously, AI can only process inputs that it is designed to recognize and analyze. Without human intervention in the form of an auxiliary program, a translation AI cannot evaluate images. The data would appear nonsensical to it. One day, AIs may be able to write their own code. For now, efforts to design such AIs are nascent and speculative. Even then, however, AIs would not likely be self-reflective. Their objective functions would still define them. They might write code the way AlphaZero plays chess, brilliantly, but without reflection or volition, with strict adherence to the rules. Wither AI. The advances in machine learning algorithms, combined with increasing data and computational power, have enabled rapid progress in the application of AI, capturing imaginations and investment dollars. The explosion of the research, development, and commercialization of AI, especially machine learning, is global. but it has largely been concentrated in the United States and China. Universities, laboratories, startups, and conglomerates in both countries have been at the forefront of developing and applying machine learning to ever more complex problems. That said, many aspects of AI and machine learning still need to be developed and understood. Machine learning-powered AI requires substantial training data. Training data, in turn, requires substantial computing infrastructure, making retraining AI prohibitively expensive, even if it is otherwise desirable to do so. With data and computing requirements limiting the development of more advanced AI, devising training methods that use less data and less computer power is a critical frontier. Furthermore, despite major advances in machine learning, complex activities that require synthesizing several tasks remain challenging for AI. Driving a car, for example, has proved a formidable challenge, requiring the performance of functions from visual perception to navigation to proactive accident avoidance, all simultaneously. While the field has advanced tremendously over the past decade, driving scenarios vary significantly in terms of how challenging it is to reach human-level performance. Currently, AIs can achieve good performance in structured settings such as limited access highways and suburban streets with few pedestrians or cyclists. Operating in chaotic settings such as a city's rush hour traffic, however, remains challenging. Highway driving is particularly interesting, since human drivers in that setting often become bored and distracted, making it possible that AIs could be safer than human drivers for long-distance travel in the not-too-distant future. Predicting the rate of AI's advance will be difficult. In 1965, engineer Gordon Moore predicted computing power would double every 2 years, a forecast that has proved remarkably durable. But AI progresses far less predictably. Language translation AI stagnated for decades, then, through a confluence of techniques and computing power, advanced at a breakneck pace. In just a few years, humans developed AIs with roughly the translation capacity of a bilingual human. How long it will take AI to achieve the qualities of a gifted professional translator, if it ever does, cannot be predicted with precision. Forecasting how swiftly AI will be applied to additional fields is equally difficult. But we can continue to expect dramatic increases in the capacities of these systems. Whether these advances take 5, 10, or 25 years, at some point, they will occur. Existing AI applications will become more compact, effective, inexpensive, and, therefore, more frequently used. AI will increasingly become part of our daily lives, both visibly and invisibly. It is reasonable to expect that over time, AI will progress at least as fast as computing power has, yielding a million-fold increase in 15 to 20 years. Such progress will allow the creation of neural networks that, in scale, are equal to the human brain. As of this writing, generative transformers have the largest networks. GPT-3 has about 1,011 such weights. But recently, the state-funded Beijing Academy of Sciences announced a generative language model with 10 times as many weights as GPT-3. This is still 104 times fewer than estimates of the human brain's synapses. But if advances proceed at the rate of doubling every 2 years, this gap could close in less than a decade. Of course, scale does not translate directly to intelligence. Indeed, the level of capability a network will sustain is unknown. Some primates have brains similar in size to or even larger than human brains, but they do not exhibit anything approaching human acumen. Likely, development will yield AI savants, Programs capable of dramatically exceeding human performance in specific areas, such as advanced scientific fields. The dream of artificial general intelligence. Some developers are pushing the frontiers of machine learning techniques to create what has been dubbed artificial general intelligence, AGI. Like AI, AGI has no precise definition. However, it is generally understood to mean AI capable of completing any intellectual task humans are capable of, in contrast to today's narrow AI, which is developed to complete a specific task. Even more than for current AI, machine learning is critical to the development of AGI, though practical limitations may limit the extent of its expertise to a discrete number of fields, just as the most well-rounded human must still specialize. One possible path to the development of AGI involves training traditional AIs in several fields, then effectively combining their base of expertise into a single AI. Such an AGI might be more well-rounded, able to perform a broader set of activities, and less brittle, blundering less dramatically at the edges of its expertise. However, scientists and philosophers disagree about whether true AGI is even possible and about what characteristics it might entail. If AGI is possible, will it possess the capacities of an average human or of the best human in a given field? In any case, even if AGI could be developed in the manner described above, by combining traditional AIs, training them narrowly and deeply, and gradually agglomerating them to develop a broader base of expertise, it would pose challenges to even the best funded and most sophisticated researchers. Developing such AIs would require massive computation power and be extremely expensive, with current technology on the order of billions, so few could afford to create them. Regardless, it is not obvious that the creation of AGI would substantially alter the trajectory machine learning algorithms have set humanity on. Whether AI or AGI, human developers will continue to play an important role in creation and operation. The algorithms, training data, and objectives for machine learning are determined by the people developing and training the AI, thus they reflect those people's values, motivations, goals, and judgment. Even as machine learning techniques become more sophisticated, these limitations will persist. Whether AI stays narrow or becomes general, it will become more prevalent and more potent. As development and deployment costs decrease, automated devices run by AI will become readily available. Indeed, in conversational interfaces such as Alexa, Siri, and Google Assistant, they already are. Vehicles, tools, and appliances will increasingly be equipped with AIs that automate their activity under our direction and supervision. AIs will be embedded in applications on digital devices and the Internet, guiding consumer experiences and revolutionizing enterprises. The world we know will become both more automatic and more interactive, between humans and machines, even if it is not populated with the multipurpose robots of science fiction movies. In the most striking outcomes, human lives will be saved. Self-driving vehicles will reduce auto deaths. Other AIs will identify diseases earlier and more precisely. Still other AIs will discover drugs and drug delivery methods in ways that lower research costs, resulting, we hope, in the development of treatments for tenacious maladies and cures for rare diseases. AI aviators will pilot or co-pilot fleets of delivery drones and even fighter jets. AI coders will complete programs sketched by human developers. AI writers will complete advertisements conceived by human marketers. The efficiency of transportation and logistics will increase, potentially dramatically. AI will reduce energy use and likely find other ways to moderate humans' environmental impact. In the domains of both peace and war, its material effects will be startling. but its social repercussions are difficult to predict. Consider language translation. Universal translation of spoken language and text will facilitate communication as never before. Such translation will boost commerce and allow unparalleled cross-cultural exchange. And yet this new capability will also carry with it new challenges. Much as social media not only enabled the exchange of ideas but also encouraged polarization, promulgated misinformation, and disseminated hate speech, automated translation may bring languages and cultures together with explosive effects. For centuries, diplomats have carefully managed cross-cultural contact to avoid accidental offense, just as cultural sensitization has often accompanied linguistic training. Instantaneous translation eliminates these buffers. Societies may inadvertently find themselves giving offense and being offended. Will people, relying on automatic translation, exert less effort trying to understand other cultures and nations, increasing their natural tendency to see the world through the lens of their own culture? Or might people become more intrigued by other cultures? Can automatic translation somehow reflect differing cultural histories and sensibilities? Likely there will be no single answer. The most advanced AIs require vast data, tremendous computing power, and skilled technicians. Unsurprisingly, organizations with access to such resources, both commercial and governmental, drive much of the innovation in this new field. And to leaders, more resources flow. Thus, a cycle of concentration and advancement has defined AI, shaping the experience of individuals, companies, and nations. In many areas, from communication to commerce to security to human consciousness itself, AI will transform our lives and futures. We must all ensure that AI is not created in isolation, and accordingly, pay attention to both its potential benefits and its potential risks. Chapter 4. Global Network Platforms. Fictional visions of the future of AI technology tend to invoke images of sleek, fully automated self-driving cars and sentient robots that coexist with humans in homes and workplaces, conversing with their users with uncanny intelligence. Inspired by such science fiction scenes, popular conceptions of AI often involve machines that develop a seeming self-awareness, inevitably leading them to misunderstand, decline to obey, or eventually rise up against their human creators. But the anxieties underlying such common fantasies are mistaking the issue by assuming that AI's culmination will be to act like individual humans. We would be better served by recognizing that AI is already all around us, often in ways that are not entirely evident, and redirecting our technological anxieties toward encouraging greater understanding of and transparency regarding AI's integration into our lives. Social media, web searches, streaming video, navigation, ride-sharing, and countless other online services could not operate as they do without the extensive and growing use of AI. By using these online services for the basic activities of daily life, to offer product and service recommendations, select routes, make social connections, and arrive at insights or answers, people around the world are participating in a process that is both mundane and revolutionary. We rely on AI to assist us in pursuing daily tasks without necessarily understanding precisely how or why it is working at any given moment. We are forming new types of relationships that will have substantial implications for individuals, institutions, and nations, between AI and people, between people using AI-facilitated services, and between the creators and operators of these services and governments. Without significant fanfare, or even visibility, we are integrating non-human intelligence into the basic fabric of human activity. This is unfolding rapidly and in connection with a new type of entity we call network platforms, digital services that provide value to their users by aggregating those users in large numbers, often at a transnational and global scale. In contrast to most products and services, whose value to each user is independent of, or even diminished by, the presence of other users, a network platform's value and attractiveness grows as additional users adopt it, a process economists would label a positive network effect. As more users are drawn to select platforms, such gatherings tend to result in a small number of providers offering a given service, each with a large base of users, sometimes hundreds of millions or even billions. These network platforms increasingly rely on AI, producing an intersection between humans and AI on a scale that suggests an event of civilizational significance. As AI assumes greater roles on more varied network platforms, these platforms' basic manifestations are becoming material for headlines and geopolitical maneuvers, shaping aspects of individuals' daily reality. Without additional means of explanation, discussion, and oversight that are compatible with a society's values and conducive to some degree of social and political consensus, a rebellion may unfold against the advent of new and seemingly impersonal and inexorable forces, as with the rise of Romanticism in the 19th century and the explosion of radical ideologies in the 20th. Before significant disruption arises, governments, network platform operators, and users must consider the nature of their goals, the basic premises and parameters of their interactions, and the type of world they aim to create. In less than a generation, the most successful network platforms have brought together user bases larger than the populations of most nations, and even some continents. However, large user populations gathered on popular network platforms have more diffuse borders than those of political geography, and network platforms are operated by parties with interests that may differ from those of a nation. Operators of network platforms do not necessarily think in terms of government priorities or national strategy, particularly if those priorities and strategies might conflict with serving their customers. Such network platforms may host or facilitate economic and social interactions that surpass, in number and scale, those of most countries, despite the platforms having formed no economic or social policy as a government would have. Thus, although they are operated as commercial entities, some network platforms are becoming geopolitically significant actors by virtue of their scale, function, and influence. Many of the most significant network platforms originated in the United States: Google, Facebook, Uber, or China, Baidu, WeChat, Didi Chuxing. As a result, these network platforms seek to build their user bases and commercial partnerships in regions containing markets that are commercially and strategically significant to Washington and Beijing. Such dynamics introduce novel factors into foreign policy calculations. Commercial competition between network platforms can affect geopolitical competition between governments, sometimes even topping the agenda in diplomacy. This is further complicated by the fact that network platform operators' corporate cultures and strategies are often developed to reflect the priorities of customers and of research and technology hubs, both of which may be far from national capitals. In countries where they operate, certain network platforms have become integral to individual life, national political discourse, commerce, corporate organization, and even government functions. Their services, even ones that did not exist in any form until recently, now appear indispensable. As an entity without a single direct precedent from prior eras, network platforms sometimes sit in ambiguous relation to rules and expectations that were largely developed in a pre-digital world. The question of how network platforms establish community standards, the rules set by each operator, often administered with the assistance of AI, governing what content is permissible to create and share, provides a crystallizing example of the incongruity between the modern digital space and traditional rules and expectations. Although in principle most network platforms are content agnostic, in some situations their community standards become as influential as national laws. Content that a network platform and its AI permit or favor may rapidly gain prominence. Content they diminish or sometimes even outright prohibit may be relegated to obscurity. Material that is determined to contain disinformation or violate other content standards may effectively be removed from public circulation. Issues such as these have arisen swiftly in part because network platforms, and their AI, have rapidly expanded in a digital world that transcends geography. These platforms connect large groups of users across space and time, with instantaneously accessible aggregations of data, in a way that few other human creations approximate. To compound the challenge, once AI has been trained, it typically acts faster than the speed of human cognition. These phenomena are inherently neither positive nor negative. They are realities occasioned by the problems human beings seek to solve, the needs we desire to fulfill, and the technology we create to serve our ends. We are experiencing and facilitating changes that require our attention, in thought, culture, politics, and commerce, well beyond the scope of a single human mind or particular product or service. When the digital world began to expand decades ago, there was no expectation that creators would or should develop a philosophical framework or define their fundamental relationship to national or global interests. After all, such claims generally had not been made on other industries. Instead, society and governments assessed digital products and services in terms of what worked. Engineers sought practical and efficient solutions, connecting users to information and online social spaces, passengers to cars and drivers, and customers to products. There was general excitement about new capabilities and opportunities. There was little demand for predictions about how these virtual solutions might affect the values and behavior of entire societies, such as patterns of vehicle use and traffic congestion with ride-sharing or the real-world political and geopolitical alignments of national institutions with social media. AI-enabled network platforms were created even more recently, with less than a decade of development. We have yet to establish even the basic vocabulary and concepts for an informed debate about this technology, a gap this book seeks to help remedy. Various individuals, corporations, political parties, civic organizations, and governments will inevitably have differing views on the proper operation and regulation of AI-enabled network platforms. What seems intuitive to the software engineer may be perplexing to the political leader or inexplicable to the philosopher. What the consumer welcomes as a convenience the national security official may view as an unacceptable threat, or the political leader may reject as out of keeping with national objectives. What one society may embrace as a welcome guarantee another may interpret as a loss of choice or freedom. The nature and scale of network platforms is bringing the perspectives and priorities of different worlds together in complex alignments, sometimes creating tension and mutual perplexity. In order for individual, national, and international actors to reach informed conclusions about their relationship to AI, and to one another, we must seek a common frame of reference, beginning with establishing terms for informed policy discussions. Even if our understandings differ, we must aim to understand AI-enabled network platforms by assessing their implications for individuals, companies, societies, nations, governments, and regions. We must act urgently on each level. Understanding network platforms. Network platforms are inherently large-scale phenomena. One of the defining characteristics of a network platform is that the more people it serves, the more useful and desirable it becomes to users. AI is becoming increasingly important to network platforms that aim to deliver their services at scale, and as a result, nearly every internet user today encounters AI, or at least online content shaped by AI, numerous times a day. For example, Facebook, like many other social networks, has developed increasingly specific community standards for the removal of objectionable content and accounts, listing dozens of categories of prohibited content as of late 2020. Because the platform has billions of active monthly users and billions of daily views, the sheer scale of content monitoring at Facebook is beyond the capabilities of human moderators alone. Despite Facebook reportedly having tens of thousands of people working on content moderation, with the objective of removing offensive content before users see it, the scale is simply such that it cannot be accomplished without AI. Such monitoring needs at Facebook and other companies have driven extensive research and development in an effort to automate text and image analysis by creating increasingly sophisticated machine learning, natural language processing, and computer vision techniques. For Facebook, the number of removals is currently on the order of roughly 1 billion fake accounts and spam posts per quarter, as well as tens of millions of pieces of content involving nudity or sexual activity, bullying and harassment, exploitation, hate speech, drugs, and violence. In order to carry out such removals accurately, human-level judgment is often required. Thus, for the most part, Facebook's human operators and users rely on AI to determine which content warrants consumption or review. While only a small fraction of removals are appealed, those that are tend to be automated removals. Likewise, AI plays a significant role in Google's search engine, but a role that is relatively recent and rapidly evolving. Originally, Google's search engine relied on highly intricate, human-developed algorithms to organize, rank, and guide users toward information. These algorithms amounted to a set of rules for handling potential user queries. Where results didn't prove useful, human developers could adjust them. In 2015, Google's search team moved from using these human-developed algorithms to implementing machine learning. This change led to a watershed moment. Incorporating AI has vastly improved the quality and usability of the search engine, making it better able to anticipate questions and organize accurate results. Despite significant improvements in Google's search engine, however, developers had a relatively vague understanding of why searches were producing particular results. Humans can still guide and adjust the search engine, but they may not be able to explain why one particular page is ranked higher than another. To achieve greater convenience and accuracy, human developers have had to willingly forego a measure of direct understanding. As these examples illustrate, the leading network platforms increasingly depend on AI to deliver services, fulfill customer expectations, and meet various government requirements. As AI becomes increasingly critical to network platforms' functioning, it is also becoming, gradually and unobtrusively, a sorter and shaper of reality, and, in effect, an actor on the national and global stage. The potential social, economic, political, and geopolitical influence of each major network platform, and its AI, is substantially augmented by its degree of positive network effects. Positive network effects occur for information exchange activities in which the value rises with the number of participants. When the value rises in this manner, success tends to produce further success and a greater likelihood of eventual predominance. People naturally gravitate toward existing gatherings, which leads to larger aggregations of users. For a network platform relatively unconstrained by borders, this dynamic leads to a broader, often transnational geographic scope with correspondingly few major competing services. Positive network effects did not originate with network platforms. Prior to the rise of digital technology, however, the occurrence of such effects was relatively rare. Indeed, for a traditional product or service, an increase in the number of users can easily detract from rather than add to its value. This situation can produce scarcity, for a product or service that is in high demand or sold out, delays, for a product or service that cannot be delivered simultaneously to all the customers who want it, or a loss in the sense of exclusivity that gave a product its initial cachet, example, a luxury item that becomes less sought after when it is widely available. The classic example of positive network effects arises in markets themselves, be they for goods or stocks. Since at least the early 17th century, traders of Dutch East India stocks and bonds gathered in Amsterdam, where stock exchanges provided a means for buyers and sellers to arrive at a common valuation in order to trade securities. With the active participation of more buyers and sellers, a stock exchange becomes more useful and valuable to individual participants. Having more participants increases the chances that a transaction will occur and that its valuation will be accurate, given that the transaction reflects a larger number of individual negotiations between buyers and sellers. Once a stock exchange has gathered a critical mass of users in a given market, it tends to become the first stop for new buyers and sellers, leaving little incentive or opportunity for another exchange to compete by offering precisely the same service. When traditional telephones were first developed, telephone networks also demonstrated strong positive network effects. For a telephone service reliant on physical wires to connect calls, having a larger number of other subscribers on the same network creates higher value for each subscriber. Thus, in the early days of telephony, there was strong growth for large service providers. In the United States, universality was initially achieved with one very large network operated by AT&T, originally Bell Telephone, interconnected to a number of smaller, largely rural providers. By the 1980s, technological advances permitted telephone service providers to more readily connect with one another, thereby enabling subscribers of new providers to seamlessly reach those on any domestic service. These advances facilitated the regulatory breakup of AT&T, demonstrating to customers that value would remain high even without a single large provider. As technology continued to evolve, customers could reach anyone from their phones regardless of their providers, vastly reducing the positive network effect. There is no inherent reason for the dynamic of positive network effects to stop at national or regional borders, and network platforms often expand across such terrestrial boundaries. Physical distances and national or linguistic differences are rarely obstacles to expansion. The digital world is accessible from anywhere with internet connectivity, and network platform services can typically be delivered in several languages. The main limitations on expansion are those put in place by governments or perhaps technological incompatibility, the former sometimes encouraging the latter. Thus, for each type of service, such as social media and video streaming, there are generally a small number of global network platforms, perhaps complemented by local ones. Their users benefit from, and contribute to, a new, as yet poorly understood phenomenon, the operation of non-human intelligence at global scale. Community, daily life, and network platforms. The digital world has transformed our experience of daily life. As an individual navigates throughout the day, he or she now benefits from, and contributes to, vast shoals of data. The extent of this data and the options for consuming it are too immense and varied for human minds alone to process. The individual comes to rely, often instinctively or subconsciously, on software processes to organize and cull necessary or useful information, selecting news items to view, movies to watch, and music to play based on a combination of previous individual choices and broadly popular selections. Experiencing such automated curation can be so simple and satisfying that it is only noticed in its absence. For example, try reading news in someone else's Facebook feed or browsing movies using someone else's Netflix account. AI-enabled network platforms have accelerated this integration process and deepened the connections between individuals and our digital technology. With AI designed and trained to intuit and address human questions and goals, a network platform can become a guide to, interpreter for, and record of options that the human mind once managed itself, albeit less efficiently. Network platforms perform these tasks by aggregating information and experiences on a much broader scale than a single human mind or lifespan can accommodate, allowing them to produce answers and recommendations that can seem uncannily apparent. When considering the purchase of winter boots, for example, even the most dedicated individual shopper would never assess hundreds of thousands of national and regional purchases of similar items, consider recent weather trends, factor in the time of year, review his or her comparable prior searches, and investigate shipping patterns before deciding which pair of boots would be the best purchase. An AI, however, might very well assess all these factors. As a result, individuals often relate to AI-driven network platforms in a manner that they have not, historically, related to other products, services, or machines. As the individual interacts with the AI, and as the AI adapts to the individual's preferences, internet browsing and search queries, travel history, apparent income level, social connections, a kind of tacit partnership begins to form. The individual comes to rely on such platforms to perform a combination of functions that have traditionally been distributed to businesses, governments, and other humans, becoming a combination of postal service, department store, concierge, confessor, and friend. The relationship between an individual, a network platform, and its other users is a novel combination of intimate bond and remote connection. Already, AI-enabled network platforms review substantial amounts of user data, much of which is personal, such as location, contact information, networks of friends and associates, and financial and health information. Users turn to AI as a guide or facilitator of a personalized experience. The AI's precision and acuity derive from its ability to review and react to an aggregation of hundreds of millions of similar relationships and trillions of similar interactions across space, the geographic breadth of the user base, and time, the aggregation of past uses. The network platform users and its AI enter into a form of compact, interacting with and learning from each other. At the same time, a network platform's AI follows a logic that is non-human and, in many ways, inscrutable to humans. For example, in practice, when an AI-enabled network platform is assessing an image, social media post, or search query, humans may not understand precisely how the AI operates in that particular situation. While Google's engineers know that their AI-enabled search function produced clearer results than it would have without AI, they could not always explain why one particular result was ranked higher than another. To a large extent, AI is judged by the utility of its results, not the process used to reach those results. This signals a shift in priorities from earlier eras, when each step in a mental or mechanical process was either experienced by a human being, a thought, a conversation, an administrative process, or could be paused, inspected, and repeated by human beings. For example, in much of the industrialized world, the recollection is already fading of an era when travel required getting directions, a manual process that might involve an advance phone call to the person being visited, review of a printed city or state map, and, not infrequently, a stop at a gas station or convenience store to validate an assumption or correct a mistake. Now the traveling process unfolds vastly more efficiently through the use of smartphone map applications. Not only can such apps assess several possible routes and the time each would take based on what they know about historic traffic patterns at that time of day, they can also factor in accidents and other unique delays on that day, including those that occur during the drive, as well as other indicia, such as other users' searches, that traffic may become worse along a given route during the time the user will take to travel that route. The shift from atlases to online navigation services has proved so convenient that few have paused to consider what a revolutionary change has occurred or what its consequences might be. The individual and society have gained convenience by entering into a new relationship with a network platform and its operator, accessing and becoming part of an evolving dataset, including tracking of the individual's location, at least while the application is in use, and trusting the network platform and its algorithms to produce accurate results. In a sense, the individual using such a service is not driving alone. Instead, he or she is part of a system in which human and machine intelligence are collaborating to guide an aggregation of people through their individual routes. The prevalence of this type of constant AI companion is likely to increase, as sectors including healthcare, logistics, retail, finance, communications, media, transportation, and entertainment produce comparable advances, often enabled by network platforms. Our experience of day-to-day reality is being transformed. When users turn to AI-enabled network platforms for assistance with tasks, they are benefiting from a type of gathering and distilling of information that no prior generation has experienced. Such platform scale, power, and ability to pursue novel patterns provides individual users with unprecedented conveniences and capabilities. At the same time, these users are entering into a form of human-machine dialogue that has never before existed. AI-enabled network platforms have the capacity to shape human activity in ways that may not be clearly understood, or are even clearly definable or expressible, by the human user. This raises essential questions: with what objective function is such AI operating? And by whose design, and within what regulatory parameters? The answers to these and similar questions will continue to shape lives and societies in the future. Who operates and defines limits on these processes? What impact might they have on social norms and institutions? And who, if anyone, has access to what AI perceives? If no human can ever fully understand or view the data at an individualized level, or access all the steps involved in the process, that is, if the human role remains confined to designing, monitoring, and setting general parameters for AI, should such limitations be comforting, unnerving, or both? Companies and nations. Designers did not set out with the clear objective of inventing AI-enabled network platforms. Instead, they arose incidentally, as a function of the problems that individual companies, engineers, and their customers sought to solve. Network platform operators developed their technology to fulfill certain human needs. They connected buyers and sellers, inquirers and information providers, and groups of individuals sharing common interests or goals. They deployed AI to improve, or, increasingly, to enable, their services and to augment their ability to meet users, and sometimes governments' expectations. As network platforms have grown and evolved, some have incidentally come to affect activities and sectors of society well beyond their original focus. And, as previously noted, individuals have come to trust certain AI-driven network platforms with information that they would hesitate to show to a friend or the government, such as comprehensive records of where they have gone, what they did, and with whom, and what they searched for and viewed. The dynamic enabled by access to such personal data puts network platforms, their operators, and the AI they employ in newfound positions of social and political influence. Particularly during a pandemic-influenced era of social distancing and remote work, societies have come to rely on some AI-enabled network platforms as a kind of essential resource and social glue, a facilitator of expression, commerce, food delivery, and transportation. These changes have unfolded at a scale and speed that, thus far, have outpaced a broader understanding and consensus about the roles of these network platforms in society and on the international stage. As the recent role of social media in conveying and moderating political information and disinformation has demonstrated, some network platforms have assumed functions so significant as to potentially influence the conduct of national governance. This influence has arisen in effect by accident, without necessarily being sought out or properly prepared for. Yet the skills, instincts, and conceptual insights that produce excellence in the world of technology do not inevitably coincide with those of the world of government. Each sphere has its own language, organizational structures, animating principles, and core values. A network platform operating according to its standard commercial objectives and the demands of its users may, in effect, be transcending into the realm of governance and national strategy. In turn, traditional governments may struggle to discern the platform's motives and tactics even as they seek to adjust them to national and global objectives. The fact that AI operates according to its own processes, which are different from and often faster than human mental processes, adds another complexity. AI develops its own approaches for fulfilling whatever objective functions were specified. It produces outcomes and answers that are not characteristically human and that are largely independent of national or corporate cultures. The global nature of the digital world, and AI's ability to monitor, block, tailor, produce, and distribute information on network platforms worldwide, imports these complexities to the information space of disparate societies. As increasingly sophisticated AI is used to enable network platforms, it shapes social and commercial arrangements on a national and global scale. While social media platforms, and their AI, generally represent themselves as content agnostic, not only their community standards but also their filtering and presentation of information can influence the way that information is created, aggregated, and perceived. As AI operates to recommend content and connections, categorize information and concepts, and predict user preferences and goals, it may inadvertently reinforce particular individual, group, or societal choices. In effect, it may encourage the distribution of certain types of information and the formation of certain types of connections, while discouraging others. This dynamic potentially affects social and political outcomes, regardless of the platform operator's intentions. Each day, individual users and groups influence one another rapidly and at vast scales across countless interactions, particularly when shaped by complex, AI-driven recommendations. As a result, Operators may not have a clear understanding of what is occurring in real time. And the complexities are magnified if the operator injects, wittingly or unwittingly, their own values or purposes. Recognizing these challenges, governmental attempts to address these dynamics will need to proceed with great care. Any governmental approach to this process, whether to restrict, control, or permit it, necessarily reflects choices and value judgments. If a government encourages platforms to label or block certain content, or if it requires AI to identify and downgrade biased or false information, such decisions may effectively operate as engines of social policy with unique breadth and influence. Across the world, the way to address these choices has become the subject of searching debates, particularly in technologically advanced free societies. Any approach is guaranteed to play out on a scale that is vastly greater than nearly any past legal or policy decision, with potentially instantaneous effects on the daily lives of millions or billions of users in many governmental jurisdictions. The intersection between network platform and governmental arenas will produce unpredictable and, in some cases, highly contested results. Rather than clear outcomes, however, we are more likely to arrive at a series of dilemmas with imperfect answers. Will attempts to regulate network platforms and their AIs function in alignment with various nations' political and social goals? Example, reducing crime, combating bias, and ultimately produce more just societies? Or will they lead to more powerful and intrusive governments that shape outcomes through a machine proxy, the logic of which is ineffable and the conclusions of which become unavoidable? In iterative exchanges taking place over time, across continents, and between supranational user bases, will AI-driven network platforms advance a shared human culture and quest for answers beyond any national culture or value system? Or will AI-enabled global network platforms amplify specific lessons or patterns divined from users, producing effects that differ from, or even undermine, those their human developers planned or anticipated? We cannot avoid answering these questions because our communications, as now constructed, can no longer operate without AI-assisted networks. Network platforms and disinformation. National borders have long been permeable to new ideas and trends, including those fostered with a deliberately malign purpose, but never at such scale. While there is broad consensus regarding the importance of preventing intentionally distributed malign disinformation from driving social trends and political events, ensuring this outcome has rarely proved to be a precise or entirely successful undertaking. Moving forward, however, both offense and defense, both the spread of disinformation and efforts to combat it, will become increasingly automated and entrusted to AI. The language-generating AI GPT-3 has demonstrated the ability to create synthetic personalities, use them to produce language that is characteristic of hate speech, and enter into conversations with human users in order to instill prejudice and even urge them toward violence. If such an AI were to be deployed to spread hate and division at scale, humans alone may not be capable of combating the outcome. Unless such AI is arrested early in its deployment, manually identifying and disabling all its content through individual investigations and decisions would prove deeply challenging for even the most sophisticated governments and network platform operators. For such a vast and arduous task, they would have to turn, as they already do, to content moderation AI algorithms. But who creates and monitors these and how? When a free society relies on AI-enabled network platforms to generate, transmit, and filter content across national and regional borders, and when those platforms proceed in a manner that inadvertently promotes hate and division, that society faces a novel threat that should prompt it to consider novel approaches to policing its information environment. The underlying problem is urgent, yet AI-reliant solutions produce their own critical questions. We must not forego consideration of the proper balance between human judgment and AI-driven automation on both sides of the equation. For societies accustomed to the free exchange of ideas, grappling with AI's role in assessing and potentially censoring information has introduced difficult fundamental debates. As the tools for spreading disinformation become more powerful and increasingly automated, the process of defining and suppressing disinformation increasingly appears as an essential social and political function. For private corporations and democratic governments, this role brings not only an unusual but also a frequently unsought degree of influence and responsibility over shifts in social and cultural phenomena, developments that previously had not been operated or controlled by any single actor, but had developed across millions of individual interactions in the physical world. For some, the inclination will be to entrust the task to a technical process that seems free from human bias and partiality, an AI with an objective function to identify and arrest the flow of disinformation and falsity. But what of the content that is never viewed by the public? When the prominence or diffusion of a message is so curtailed that its existence is, in effect, negated, we have reached a state of censorship. If anti-disinformation AI makes a mistake, suppressing content that is not malign disinformation but in fact authentic, how do we identify it? Can we know enough, and in time, to correct it? Alternatively, do we have the right to read, or even a legitimate interest in reading, AI-generated, false information? The power to train defensive AI against an objective, or subjective, standard of falsehood, and the ability, if any can be developed, to monitor that AI's operations, would in itself become a function of importance and influence rivaling the roles traditionally held by government. Small differences in the design of an AI's objective function, training parameters, and definitions of falsehood could lead to society-altering differences in outcome. These questions become all the more vital as network platforms use AI to provide their services to billions of people. The international political and regulatory debates over TikTok, an AI-enabled network platform for the creation and sharing of short, often whimsical videos, offers an unexpected early glimpse of the challenges that can arise when relying on AI to shape communications, particularly when that AI is developed in one nation and used by citizens of another. Users of TikTok film and post videos with their smartphones, and many millions of users enjoy watching them. Proprietary AI algorithms recommend content those individuals might enjoy based on their previous use of the platform. Developed in China and having become popular globally, TikTok neither creates content nor appears to set extensive restrictions on it, beyond a time limit on videos and community guidelines that prohibit misinformation, violent extremism, and certain types of graphic content. To the general viewer, the primary attribute of TikTok's AI-assisted lens on the world appears to be whimsicality. Its content consists primarily of silly short video snippets of dances, jokes, and unusual skills. Yet because of government concerns about the application's collection of user data and its perceived latent capacity for censorship and disinformation, both the Indian and American governments moved to restrict TikTok's use in 2020. Further, Washington moved to force the sale of TikTok's U.S. operations to a U.S.-based company that could hold user data domestically, preventing it from being exported to China. In turn, Beijing acted to prohibit the exportation of the code that supported the content recommendation algorithm, at the heart of TikTok's efficacy and user appeal. Soon, more network platforms, perhaps most of those that enable communication, entertainment, commerce, finance, and industrial processes, will rely on increasingly sophisticated, tailor-made AI to deliver key functions and moderate and shape content, often across national borders. The political, legal, and technological ramifications of these maneuvers are still unfolding. That a single AI-enabled whimsical entertainment application has prompted such official multinational consternation suggests that more complex geopolitical and regulatory riddles await us in the near future. Governments and regions. Network platforms pose new cultural and geopolitical conundrums not only for individual countries but also, given the natural borderlessness of such technology, for relations between governments and broader regions. Even with substantial and sustained government intervention, most countries, even technologically advanced ones, will not give rise to companies that produce or maintain an advanced national version of each globally influential network platform, such as those used for social media, web search, and so on. The pace of technological change is too rapid, and the number of knowledgeable programmers, engineers, and product design and development professionals too few, for such broad coverage. The global demand for talent is too high, the local markets for most services too small, and the product and service costs too substantial to maintain an independent version of each network platform. To stay at the evolving forefront of technological development requires intellectual and financial capital, beyond what most companies possess, and beyond what most governments are willing or able to provide. But even in such a scenario, many users, if given the choice, would rather not be limited to a network platform that hosts only their compatriots and the software offerings and content they produce. Instead, the dynamics of positive network effects will tend to support only a handful of participants who are leading the technology and the market for their particular product or service. Many nations are, and are likely to remain indefinitely, reliant on network platforms that are both designed and hosted in other countries. Thus they are also likely to remain, at least in part, dependent on other countries' regulators for continued access, key inputs, and international updates. Therefore, many governments will have an incentive to guarantee the continued operation of AI-driven online services from other countries that have already been incorporated into fundamental aspects of their society. This undertaking may take the form of regulating network platforms' owners or operators, instituting requirements for their operation, or managing the training of their AI. Governments might insist that developers include steps to avoid certain forms of bias or address particular ethical quandaries. Public figures may succeed in leveraging a network platform and its AI to obtain greater visibility for their content, enabling them to reach larger audiences. But if platform operators decide that such prominent figures have violated content standards, they can readily be censored or removed, rendering them unable to reach such broad audiences, or driving their audiences underground. Or their content could be accompanied by some form of warning label or other potentially stigmatizing qualification. The issue is what person or institution should make that decision. The authority to independently make and enforce such judgments, now resting with some companies, reflects a level of power that few democratic governments have wielded. While most people would consider it undesirable for private companies to have this degree of power and control, ceding it to government bodies would be almost equally problematic. We have moved beyond conventional policy approaches. When it comes to network platforms, the necessity for such assessments and decisions has arisen swiftly and almost accidentally in recent years, seeming to have surprised users, governments, and companies alike. It needs to be resolved. Network platforms and geopolitics. The emerging geopolitics of network platforms comprises a key new aspect of international strategy, and governments are not the only players. Governments may increasingly seek to limit the use or behavior of such systems or attempt to prevent them from edging out homegrown rivals in important regions, lest a competing society or economy gain a powerful influence over that country's industrial, economic, or, more difficult to define, political and cultural development. Yet because governments generally do not create or operate these network platforms, the actions of inventors, corporations, and individual users will shape the field along with government restrictions or incentives, creating a strategic arena that is particularly dynamic and difficult to predict. Further, a new form of cultural and political anxiety is being added to this already complex equation. In Beijing, Washington, and some European capitals, concern has been expressed, and articulated obliquely elsewhere, about the implications of conducting broad aspects of national economic and social life on network platforms facilitated by AI designed in other, potentially rival, countries. From this technological and policy ferment, new geopolitical configurations are being established. The United States has given rise to a globe-spanning, technologically leading set of privately operated network platforms that rely increasingly on AI. The roots of this achievement lie in academic leadership at universities that attract top global talent, a startup ecosystem that enables participants to bring innovations rapidly to scale and profit from their developments, and government support of advanced R&D, through the National Science Foundation, DARPA, and other agencies. The prevalence of English as a global language, the creation of homegrown or US-influenced technology standards, and the emergence of a substantial domestic base of individual and corporate customers, all provide a favorable environment for US network platform operators. Some of these operators eschew government involvement and see their interests as primarily non-national, while others have embraced government contracts and programs. Abroad, they are all increasingly being treated, often without distinction, as creations and representatives of the United States, although in many cases the U.S. government's role was confined to staying out of their way. The United States has begun to view network platforms as an aspect of international strategy, restricting the domestic activities of some foreign platforms and restricting the export of some software and technology that could facilitate the growth of foreign competitors. At the same time, federal and state regulators have identified major domestic network platforms as targets for antitrust actions. In the near term, at least, this simultaneous drive for strategic preeminence and domestic multiplicity may push U.S. development in conflicting directions. China has similarly supported the development of network platforms that are already global in scale, but, at the same time, are poised to expand even further. While Beijing's regulatory approach has encouraged fierce competition among domestic technology players, with global markets as the ultimate goal, it has largely excluded, or mandated heavily tailored offerings by non-Chinese counterparts within China's borders. In recent years, Beijing has also taken steps to shape international technology standards and bar the export of sensitive, domestically developed technologies. Chinese network platforms predominate in China and nearby regions, and some are leading in global markets. Some Chinese network platforms enjoy built-in advantages within Chinese diaspora communities, Chinese-speaking communities in the United States and Europe, for example, continue to heavily use WeChat's financial and messaging functions, but their appeal is not limited to Chinese consumers. Having dominated China's rough-and-tumble domestic market, the country's preeminent network platforms and its AI technology are positioned to compete in the global market. In certain markets, such as the United States and India, governments have become increasingly outspoken regarding Chinese network platforms and other Chinese digital technology as potential or de facto extensions of the Chinese government's policy objectives. While this may be true in certain instances, the difficulties of some Chinese network platform operators suggest that company relationships with the Chinese Communist Party may be complex and varied in practice. Chinese network platform operators may not automatically reflect party or state interests. The correlation is likely to depend on particular network platforms' functions and the extent to which their operators understand and navigate unspoken governmental red lines. More broadly, while East and Southeast Asia, the home of companies with global reach, produce key technologies such as semiconductors, servers, and consumer electronics, they are also the home of locally created network platforms. Across the region, Chinese and American-hosted platforms are influential to varying degrees among varying segments of the population. In their relationships to network platforms, as in other aspects of economics and geopolitics, the countries of the region have been closely tied to the US-derived technology ecosystem. But there is also substantial use of Chinese network platforms as well as broader engagement with Chinese companies and technology, which East and Southeast Asians may regard as organically connected to their region and integral to their own economic success. Europe, unlike China and the United States, has yet to create homegrown global network platforms or cultivate the sort of domestic digital technology industry that has supported the development of major platforms elsewhere. Still, Europe commands the attention of the major network platform operators with its leading companies and universities, its tradition of Enlightenment exploration, which laid essential foundations for the computer age, its sizable market, and a regulatory apparatus that is formidable in its ability to innovate and impose legal requirements. Yet Europe continues to face disadvantages for the initial scaling of new network platforms because of its need to serve many languages and national regulatory apparatuses in order to reach its combined market. By contrast, national network platforms in the United States and China are able to start at a continental scale, allowing their companies to better afford the investment needed in order to continue scaling in other languages. The EU has recently focused regulatory attention on the terms of network platform operators' participation in its market, including these operators, and other entities, use of AI. As in other geopolitical questions, Europe faces the choice of whether to act as an ally to one side or the other in each major technological sphere, shaping its course by establishing a special relationship, or as a balancer between sides. Here, the preferences of the traditional EU states and the newer Central and Eastern European entrants may differ, reflecting varying geopolitical and economic situations. Thus far, historic global powers such as France and Germany have prized independence and the freedom to maneuver in their technology policy. However, peripheral European states with recent and direct experience of foreign threats, such as post-Soviet Baltic and Central European states, have shown greater readiness to identify with a US-led technosphere. India, while still an emerging force in this arena, has substantial intellectual capital, a relatively innovation-friendly business and academic environment, and a vast reserve of technology and engineering talent that could support the creation of leading network platforms, as has recently been demonstrated with its homegrown online shopping industry. India's population and economy are of a size that could sustain potentially independent network platforms without recourse to other markets. Likewise, Indian-designed network platforms have the potential to become popular in other markets as well. In previous decades, much of India's software talent has been deployed in the IT services industry or in non-Indian network platforms. Now, as the country assesses its regional relationships and relative reliance on imported technology, it may elect either to chart a more independent path or assume a principal role within an international bloc of technologically compatible nations. Russia, despite a formidable national tradition in math and science, so far has produced few digital products and services with consumer appeal beyond its own borders. Nevertheless, its formidable cyber capabilities and demonstrated ability to penetrate defenses and carry out operations across global networks suggest that Russia must be counted among the important technological powers of the world. Perhaps as a result of exploiting the online vulnerabilities of other countries, Russia has also fostered the use of certain network platforms on a national scale, such as search, example, Yandex. Though in their present form, these have relatively limited appeal to non-Russian consumers. Currently, these platforms function as a fallback or as an alternative to the dominant providers, not as substantial economic competitors. Shaped primarily by these governments and regions, a multidisciplinary contest for economic advantage, digital security, technological primacy, and ethical and social objectives is unfolding, although to date, the principal players have not consistently identified the nature of the contest or the rules of the game. One approach has been to treat network platforms and their AI as primarily a matter of domestic regulation. In this view, government's principal challenge is to prevent platforms from abusing their positions or shirking previously established or regulated responsibilities. These concepts are evolving and contested, particularly within and between the United States and the EU. And because of the manner in which positive network effects increase value to users with scale, such responsibilities often prove difficult to define. Another approach has been to treat network platforms' emergence and operations as primarily an issue of international strategy. In this view, the popularization of a foreign operator within a country introduces new cultural, economic, and strategic factors. There is the concern that network platforms may foster, even passively, a level of connection and influence that previously would have arisen only from a close alliance, particularly with the use of AI as a tool for learning from and influencing citizens. If a network platform is useful and successful, it comes to support broader commercial and industrial functions, and, in this capacity, it may become nationally indispensable. At least theoretically, the threatened withdrawal of such a network platform, or its key technological inputs, either by a government or a corporation, serves as a potential instrument of leverage. But by the same token as an incentive to make it dispensable. This hypothetical ability to weaponize network platforms, or other technologies, by withholding them in a crisis may prompt governments to engage in new forms of policy and strategy. For countries and regions that do not produce homegrown network platforms, the choice for their immediate future seems to be between 1. Limiting reliance on platforms that could provide leverage to an adversary government, 2. Remaining vulnerable, for example, to another government's potential ability to access data about its citizens, or 3. Counterbalancing potential threats against each other. A government may decide that the risks of allowing certain foreign network platforms to operate within its borders are unacceptable, or that they would need to be balanced by the introduction of rival network platforms. Governments with resources may choose to sponsor a domestic entrant as a rival. In many cases, however, this choice would require substantial and sustained intervention, and still risk failure. Advanced countries are likely to try to avoid depending on products of any other single country for key functions. Example: social media, commerce, ride-sharing, particularly in areas where there are several network platforms available globally. That AI-enabled network platforms created by one society may function and evolve within another society, and become inextricable from that country's economy and national political discourse marks a fundamental departure from prior eras. Previously, sources of information and communication were typically local and national in scope, and maintained no independent ability to learn. Today, transportation network platforms created in one country could become the arteries and lifeblood of another country, as the platform learns which consumers need certain products and as it automates the logistics of provision. In effect, such network platforms could become critical economic infrastructure, giving the country of origin leverage over any country that relies on it. The push and pull of individuals, companies, regulators, and national governments seeking to shape and channel AI-enabled network platforms will grow increasingly complex, conducted alternately as a strategic contest, a trade negotiation, and an ethical debate. Questions that appear urgent may be out of date by the time the relevant official participants have gathered to discuss them. By that time, the AI-enabled network platform may have learned or exhibited new behavior that renders the original terms of the discussion obsolete or insufficient. Creators and operators may come to better understand network platforms' objectives and limits, but remain unlikely to intuit probable governmental concerns or broader philosophical objections in advance. Dialogue between these sectors about core concerns and approaches is urgently needed, and should, wherever possible, take place before AI is deployed as part of large-scale network platforms. AI-enabled network platforms and our human future. Human perception and experience, filtered through reason, has long defined our understanding of reality. This understanding has typically been individual and local in scope, only reaching broader correspondence for certain essential questions and phenomena. It has rarely been global or universal, except in the distinctive context of religion. Now day-to-day reality is accessible on a global scale, across network platforms that unite vast numbers of users. Yet the individual human mind is no longer reality's sole, or perhaps even its principal, navigator. AI-enabled continental and global network platforms have joined the human mind in this task, aiding it and, in some areas, perhaps moving toward eventually displacing it. New concepts of understanding and limitations, between regions, governments, and network platform operators, must be defined. The human mind has never functioned in the manner in which the Internet era demands. With its complex effects on defense, diplomacy, commerce, healthcare, and transportation posing strategic, technological, and ethical dilemmas too complex for any one actor or discipline to address alone. The advent of AI-enabled network platforms is raising questions that should not be viewed as exclusively national, partisan, or technological in nature. Strategists need to consider the lessons of prior eras. They should not assume that total victory is possible in each commercial and technological contest. Instead, they should recognize that prevailing requires a definition of success that a society can sustain over time. This, in turn, requires answering the kinds of questions that eluded political leaders and strategic planners during the Cold War era. What margin of superiority will be required? At what point does superiority cease to be meaningful in terms of performance? What degree of inferiority would remain meaningful in a crisis in which each side used its capabilities to the fullest? Network platform operators will face choices beyond those of serving customers and achieving commercial success. Until now, they have generally not been obliged to define a national or service ethic beyond the organic drive to improve their products, increase their reach, and serve the interests of users and shareholders. As they have assumed broader and more influential roles, however, including functions that influence, and sometimes rival, the activities of governments, they will face far greater challenges. Not only will they need to assist in defining the capacity and ultimate purposes of the virtual realms they have created, they will also need to pay increasing attention to how they interact with one another and with other sectors of society.